Good morning, everyone. My name is Jesus Alberto Camescota, and it is a pleasure to present our work entitled Photocatalytic Hydrogen Production Under UV Irradiation with Modified Zinc Oxide. This research was carried out as a collaborative work between the Universidad Autónoma de Sinaloa, Mexico, and the University of Granada, Spain. Abstract. Hydrogen production through photocatalytic processes represents a promising alternative for green energy production. In this regard, zinc oxide, or ZnO, is a very promising semiconductor oxide for photocatalysis. In this work, pure ZnO and boron-modified ZnO were synthesized by mechanochemistry for use as photocatalysts for hydrogen production under UV irradiation. The structural, optical, and photoelectrochemical properties were evaluated using various characterization techniques, including X-ray diffraction, UV-vis spectroscopy, and photocurrent density measurements. The results show that boron modification affected all the evaluated properties while preserving the Wurtzite crystal structure. In particular, the band gap decreased from 3.3 electron volts for ZnO to 3.1 electron volts for BZnO. Furthermore, an increase in photocurrent density under UV irradiation was observed over time, indicating improved charge separation in the modified material. As a result, the boron-modified ZnO exhibited higher hydrogen production than pure ZnO, demonstrating its excellent performance as a photocatalyst. Introduction. Hydrogen production through photocatalytic processes represents a very promising alternative for clean energy generation. There is currently strong interest in developing technologies capable of producing hydrogen using solar energy, since hydrogen produces only water as a byproduct and can help reduce greenhouse gas emissions. Among the various semiconductor materials used for photocatalysis, zinc oxide, known as ZnO, stands out for several important advantages. First, it is an inexpensive and widely available material. In addition, it exhibits excellent thermal and chemical stability. It also has low toxicity and a highly stable Wurtzite crystal structure, which provides excellent photoelectrochemical properties. Finally, ZnO is regarded as a promising material for hydrogen production. However, ZnO also presents several important limitations. Its relatively wide band gap of approximately 3.4 electron volts means that it mainly absorbs ultraviolet light, which represents only a small fraction of the solar spectrum. Moreover, rapid recombination of photogenerated electron hole pairs significantly reduces its photocatalytic efficiency. Its relatively low electrical conductivity also limits charge transport and increases ohmic losses. As a consequence, the photocatalytic activity of pure ZnO remains limited. Why modify ZnO with boron? To overcome these limitations, we decided to incorporate boron into zinc oxide, as illustrated in the poster. Boron incorporation increases the concentration of charge carriers through the Bernstein-Moss effect. This enhances the electrical conductivity of the material, reduces ohmic resistance, and promotes a more efficient separation of photogenerated electron hole pairs. Consequently, a higher photocatalytic efficiency and enhanced hydrogen production can be expected. Methodology. To synthesize the materials, we employed a mechanochemical synthesis method. Both pure ZnO and boron-modified ZnO were prepared using zinc nitrate hexahydrate, boric acid, and polyvinyl pyrrolidone, or PVP, as precursor materials. The mechanochemical synthesis was carried out in a ball mixer mill operated for 15 minutes at 20 Hz. The resulting powders were then dried at 90 degrees Celsius for 24 hours. After drying, the samples were heat treated at 500 degrees Celsius under a nitrogen atmosphere for 2 hours. Finally, the synthesized material was ground using an agate mortar. To evaluate hydrogen production, the photocatalysts were deposited onto a metallic plate and dried. The reactor was purged with nitrogen and operated under a continuous flow of a water-methanol mixture while being simultaneously heated and irradiated with ultraviolet light. The reaction products were analyzed by gas chromatography. Results. Now I would like to present the main results of this work. Figure 1a shows the UV visible absorption spectra. The boron-modified material exhibits a slight reduction in the band gap, decreasing from approximately 3.3 electron volts for pure ZnO to 3.1 electron volts for boron-modified ZnO, which favors light absorption. Figure 1b presents the X-ray diffraction patterns. Both materials preserve the characteristic Wurtzite crystal structure, indicating that boron incorporation does not alter the crystalline phase of ZnO. Figure 1c shows the photocurrent density measured under ultraviolet irradiation. The boron-modified ZnO exhibits a significantly higher photocurrent response than pure ZnO, indicating more efficient charge separation and improved charge transport. Figure 2 summarizes the thermophotocatalytic hydrogen production experiments. As the operating temperature increases, the hydrogen production rate also increases. Furthermore, the boron-modified ZnO clearly outperforms pure ZnO in terms of both quantum efficiency and hydrogen production. These results confirm that boron incorporation enhances charge generation and separation, improves light absorption, and produces a synergistic effect that significantly increases hydrogen production. Conclusions. In conclusion, boron-modified ZnO was successfully synthesized via mechanochemical processing while preserving the quartzite crystal structure. Boron incorporation modified the optical and electronic properties of ZnO, promoting enhanced light absorption and more efficient charge separation. The BZNO system also exhibited improved photoelectrochemical performance during prolonged operation. Furthermore, thermophotocatalytic activity increased with temperature. The modified ZnO samples clearly outperformed pristine ZnO in terms of quantum efficiency and hydrogen production. This improvement is attributed to enhanced charge generation and separation, together with improved light absorption. Overall, the synergistic combination of photonic and electronic effects significantly boosted hydrogen production. Acknowledgements. The authors would like to thank the Secretaría de Ciencia y Humanidades, Tecnología y Innovación (CIST) for the support provided through the National Postgraduate and Mobility Scholarship Program. This research was also funded by the 2024 Leonardo Grant for Scientific Research and Cultural Creation from the BBVA Foundation in Spain. Thank you very much for your attention. I will be happy to answer any questions.